In the previous lecture, I have introduced two important elementary excitations, and those were phonons and rotons. Actually, as I have told you, that the elementary idea of phonons and rotons is needed to understand the Landau theory of liquid helium 2. So, previously I have introduced the elementary properties or features of phonons and rotons. Okay. Now, today we are going to start to understand the Landau theory of liquid helium 2. Actually, this theory regarding the liquid helium 2 proposed by Landau is a very elegant and very rigorous theory, and so I would like to explain this theory in very detail, and so it will take time. But if I will try to deal with the complete theory in one lecture, that will be a very long lecture and that will be not convenient for you. And that's why I am just going to divide this lecture on Landau theory of helium liquid 2 in three parts. Actually, in first part of the lecture, we will see only the basic assumptions on which this theory is based on. That is, the assumptions which was made by Landau to develop his theory, we will see in the first part of the lecture. And then in the second part of the lecture, we will find that internal energy and the specific heat capacity at constant volume for the liquid helium. Okay. And finally, in third part, we will calculate the mass density of the normal component of the helium liquid consisting of phonons and rotons in thermal equilibrium. So, this complete theory of Landau for the helium liquid 2 will be dealt in three lectures, and this is your first lecture on this theory. Okay. Now, a question definitely arises in your mind that why this Landau theory is needed. Already we have studied about the calculation of the energy and the specific heat capacity of helium liquid 2 earlier in the ideal Bose, on the basis of ideal Bose gas model. Then why a Landau theory is needed? The answer is obvious, that whenever you study any new theory regarding a concept which has been already explained by another theory, definitely in the first theory there will be some drawback, and that drawback must be removed in the new theory. So remember, you can remember that because you have already studied the calculation of the internal energy and the specific heat capacity of helium liquid 2 in the previous lecture on the basis of ideal Bose gas model. And you can remember that we have obtained that on the basis of ideal gas model, the specific heat of the helium liquid was found to be proportional to T to the power 3 by 2. It means Cv is proportional to T to the power 3 by 2. This was the result which we have obtained earlier. Okay. But when you will compare this theoretical result with the experimental result, you will find that this result does not agree with the experimental result, because experimentally it is found that particularly in the low temperature region, that is, you can say when temperature T tends towards 0 Kelvin, then experimentally it is found that Cv is proportional to T cube, as in device theory of a specific heat of solids. Similarly, in case of this condensed phase of helium liquid, which is called superfluid helium, Cv is found to be experimentally proportional to T cube. But the earlier theory predicts that Cv is proportional to T to the power 3 by 2. So you can say that the result obtained earlier on the basis of ideal gas model does not agree with the experimental result. Actually, to remove this difficulty and this drawback, Landau proposed a theory of liquid helium 2. Okay, and you will see that when we will study the Landau theory, we will see that the result obtained by Landau on theoretical basis agrees with the experimental result. That is, in accordance with Landau's theory, you will find that Cv will be proportional to T to the power 3. Okay, and so this Landau theory of liquid helium 2 is superior than the ideal Bose gas model theory. Okay, actually, to develop his theory, Landau made some assumptions. So what are the important assumptions on which this theory is based? We will discuss only these things in this first part of lecture on this subject. Okay, the main assumptions made by Landau is like this. According to him, the background fluid, that is the superfluid helium 2, you can say, in this background fluid, excitations move. And what are the excitations? Because you have learned already in the previous lecture, there will be actually two types of excitations. The first one is phonon, which is actually quantized sound wave, and another is roton. Okay, and these two excitations move in the superfluid helium. Okay, the another assumption made by Landau was that at 0 Kelvin temperature, or you can say at very low temperature, the entire liquid is in its ground state. And actually that ground state, you know, is also called superfluid phase. You have already studied the Bose-Einstein condensation, and you have seen in that condition, when T is 0 Kelvin, all the bosons, all the particles are in the ground state. There is no particle in excited state, and so the ground state forms a most condensed phase, which is called Bose-Einstein condensate. Okay, so at 0 Kelvin temperature, the complete liquid will be in its ground state, which is called superfluid phase, and the internal energy in that condition we assume is equal to U naught. Okay, but as the temperature is raised, the system moves into excited states. Okay, and the number of excited states increases with temperature. Okay, so I have mentioned it here that at T increases, the system moves to excited states. Okay, and any low excited state of a system can be regarded in quantum mechanics as an assembly of elementary excitations which just behave like quasi particles. Okay, and the quasi particles have, you know, definite energy and momenta, and they move in volume occupied by the system. Okay, and actually at very low temperature, the number of elementary excitations is sufficiently small, and so they do not interact with one another, And in this condition, the assembly of these excitations may be regarded as an ideal gas. Okay. Now, as I have told you earlier, that there are two types of excitations at very low temperature. The excitations are phonons or quantized sound waves, and the energy of a phonon depends on its momentum, and it is given by E of P equal to Cp. And this result we have already seen in the previous lecture. Here actually this P is the momentum of the phonon, and C is velocity of sound wave. Mark it, because we are talking about phonon, not photon. When this result is also valid for photon, but in that case C means velocity of electromagnetic wave in free space, but here C represents the velocity of sound wave. Okay. And the another excitations are rotons. Okay. And we have already studied the different important features of rotons in the previous lecture. And the energy of this roton is given like this. This is E of P equal to delta plus P minus P naught square over 2 mu. Here actually this delta represents the energy of the roton when its momentum is P naught. And this is actually the minimum energy of the roton. So you can also say that this delta represents the EP minimum. This is actually the minimum energy of the roton. Okay. And mu is the effective mass. Okay. In fact, if the number of phonons and rotons is not very large, okay, then the liquid helium can be regarded as a mixture of two ideal gases, a phonon gas and a roton gas. Okay. And these two excitations are assumed to be two parts of one and the same excitation energy momentum curve, which I have shown in this figure. Okay. Actually, this curve has been described in the previous lecture too, and you can see that here the energy of the excitations E of P has been plotted in against of the momentum P. And you can see the graph that this energy EP first rises linearly. See this linear part, and actually this corresponds to the equation E equal to Cp. This is just the equation of a straight line, y equal to mx. Okay. So this straight part of the curve represents the energy variation with momentum for phonons. Okay. But this increase in energy reach to the maximum value. Here you can see this is the maximum energy. Okay. This point represents the maximum energy. And after reaching to the maximum point, then the energy again starts falling. It starts decreasing. Okay. And in the process of decrement, it reaches to a point, let us say here K, and at this point K, the energy becomes minimum. This energy is minimum, and that minimum energy is represented by this symbol delta, you can see. And corresponding to this minimum energy, the momentum is P naught, you can see it here. And after this, again the energy starts increasing, and again it rises. Okay. Actually, in thermal equilibrium, the regions near the minima of this EP curve, that is near this point K, these regions are of actually of particular importance, because this in this region the excitation is not phonons but it is rotons, because you can see that the energy of rotons is given by this formula, and from this formula it is obvious that when P is equal to P naught, then you can see that this E is equal to simply delta and it is its minimum value. But if P is either greater than P naught or P is either less than P naught, in both of the cases this E will be greater than delta. E is greater than delta, okay, because this P minus P naught square will be positive even when P is less than P naught, okay. And so you can see the curve that energy is greater with respect to this point K when P is either greater than P naught or less than P naught, okay. And this curve, which represents the variation of energy of rotons, is just symmetric about this point K, which corresponds to the minimum energy of the rotons, okay. Actually, these phonons and the rotons both contribute to the thermodynamic properties of the liquid helium-2. You can't neglect the contribution of any excitation in determining the thermodynamic behavior or thermodynamic properties of the liquid helium-2. However, their relative contributions depends on temperature, okay, which the contribution of phonon or the contribution of roton, which will dominate, that depends on temperature, okay. Actually, it is seen that at sufficiently low temperature, you can say the temperature which is below 0.5 Kelvin. Actually, in this temperature region, the contribution of phonons to the thermodynamic behavior of the liquid is predominating, okay. While above 1 Kelvin temperature, the contribution of roton is relatively more important, okay. So you can say that if the temperature is less than 0.5 Kelvin, then in determining the thermodynamic properties of liquid helium-2, the contribution of phonon dominates. It means phonon determines the thermodynamic behavior of the liquid helium-2. But when temperature becomes greater than 1 Kelvin, the situation is just reverse. Now the roton's contribution is dominating. It dominates over the contribution of phonons, okay. And when you are talking about the temperature which lies between 0.5 Kelvin and 1 Kelvin, in fact, in that condition, the thermodynamic behavior of this liquid is governed by both phonons and rotons, okay. And so, in this theory, first of all, we will consider this situation, that the situation when temperature lies between 0.5 Kelvin and 1 Kelvin, when there will be the contribution of both phonons and rotons in determining the thermodynamic behavior of the liquid helium-2, okay. Now, actually, as I have told you that in this lecture we will only discuss these basic assumptions. I think you have understand what are the basic assumptions on which this Landau theory is based on. And as I have told you, our basic equations will be actually the calculation of the internal energy of this system, and after calculating the internal energy, we will calculate the specific heat capacity at constant volume, okay. And then finally we will calculate the mass density of the normal component of this liquid, okay. Now actually, to find the energy of the internal energy of this system, first of all we have to think about the bosons which constitute this superfluid helium. Actually, we suppose that the excitations, that is phonons and the rotons, are non-interacting, and this is possible at low temperature when the number of these excitations are very low. Then you can think that these excitations or these quasi particles are non-interacting bosons. Okay, and if they are non-interacting bosons, that will be just treated like an ideal gas. Okay, and the number of these particles or these uh, excitations will be not conserved. Okay, now we can find from the Bose-Einstein statistics, or we can write the expression for the mean occupation number, which is denoted by the symbol NP. I have written it inside the bracket, which represents the average value or mean value. And on the basis of Bose-Einstein statistics, you can say what will be the value of this mean value of occupation number. You know, according to Bose-Einstein statistics, this mean value of occupation number NP is equal to 1 over e to the power minus beta E of P minus 1. Here you know that this beta factor is equal to minus 1 by kT, where you know K is the Boltzmann constant. Okay, and if you want to write the total internal energy of the liquid helium, what will be the expression for that? Actually, you know that the liquid helium has two phases. In one phase, which is actually the condensed phase at low temperature, that is called the ground state, and the internal energy, we have assumed that in ground state the internal energy of this system is U naught, and the other are excited states. Okay, so the total internal energy will be the sum of the internal energy of this system in ground state and the internal energy in excited states. Okay, so U will be equal to U naught plus summation over P EP times NP. Okay, actually this EP, you know, EP is the energy of an excitation phonon or roton when its momentum is P. Okay, and NP is the average value of occupation number. So when you will multiply by this NP to EP, you will get the energy of that number of excitations. Okay, and after summing it, you will get the total energy of the excitations in the excited state. But this energy distribution is almost continuous, so actually this summation will be changed into integration. Okay, and you know that according to quantum mechanics, the number of quantum states for the momentum range between P and P plus dP is equal to what? You have studied it several times, which is called density of states, and that is actually equal to 4 pi V into P square dP. This is actually the volume in phase space, and divided by h cube. This is actually the number of quantum states in this range. And so instead of this NP, I have written here 4 pi V by h cube P square dP, and divided by e to the power minus beta EP minus 1. Okay, and in here this quasi classical idea, we consider that energy or momentum ranges from 0 to infinity. Okay, so the limits are 0 to infinity, and here actually the spin degeneracy factor GS has been taken 1, because you know that these excitations are assumed as a boson having a spin 0. So S is 0, and so GS will be equal to 2 into 0 plus 1, which is equal to 0. So GS has been not written. And this type of expression we have used earlier several times, so I hope you are getting the things. So U is equal to U naught plus 4 pi V by H cube integral 0 to infinity EP divided by e to the power minus beta EP minus 1 P squared dP. Okay. Actually here this volume V represents the geometrical volume, and so in this problem this is volume occupied by the liquid. Okay. Now actually as this system, that is the liquid helium, is in two phases. In ground state its internal energy is U naught, and in excited states there are two components of this system. First one is phonon and the another is roton. Okay. So actually you can think that the total energy of this system can be written as a sum of internal energy of the system in ground state plus internal energy of the system in excited state. But in excited state there are not photons but phonons. There are phonons and rotons. So the total internal energy can be written as U naught plus UPH plus U rot. Here actually this UPH denotes the internal energy of phonons and U rot denotes the internal energy of rotons. Okay. This is obvious. Okay. Now once you get the value of this internal energy from the definition of a specific heat, you can easily find what will be the specific heat at constant volume, because you know that Cv is equal to del U by del T at constant V. Now when you will substitute U equal to U naught plus UPH plus U rot in this equation, you know that this U naught is the internal energy of the system in ground state, which is constant. So this del U naught by del T, this will be equal to 0, and so I have not written it here. Okay. Only UPH and U rot, this will be differentiated, and when del UPH by del T at constant V and del U rot by del T at constant V, you know this represents the specific heat capacity at constant volume for phonon, and this second term represents the specific heat capacity of the roton at constant volume. So the specific heat capacity of this liquid helium, this will be simply the sum of the specific heat of phonons and the rotons. Okay. And earlier I have told you that in this lecture our aim is only to introduce the basic assumptions of this theory. Now in the second part of the theory we will calculate first of all U and then Cv. And actually for calculation, for simplicity, first of all we will consider the contribution of phonon, only phonon. It means when you will consider the contribution of phonon, you will neglect the contribution of roton, and then we will calculate this UPH. Okay. And after calculating UPH we will calculate CVPH. Okay. And then we will consider the contribution of roton only. Okay. And then you will calculate U rotation, U rot, and after calculating it we will calculate Cv rot. This will be done in the next part of the lecture. Okay. So I hope you have understand what are the basic assumptions and what is our aim in the forthcoming lecture. Okay. So this was all about the basic concept of this Landau theory. Okay.